Go. Hello, everyone. Welcome to Team 7's hydrogen fuel cell control system. My name is Michael Peterson.
My name is Ishfar Ahmed.
My name is Javier Cervantes.
My name is Anthony Malgar.
My name is Abel Milano.
And our faculty advisor is Dr. Mohammed Biswas at the University of Texas at Tyler. Let's start off with our project and what our presentation entails. We have specifications, motivations, objectives, introduction, background, why we picked the hydrogen fuel cell, how is our hydrogen fuel cell different, controlling the input and output assumptions, mass balance equation, anode and cathode energy balance equation, input variables, output state variables, block diagram, methodology, results, cost analysis, discussion, and conclusion. So in our specifications, our client told us that we had to power an 1,800 square foot home with our generator. This home consisted of 4 residents. We had to know this so that we can go into more of the calculations. And then he told us that each resident had a high energy habit. This entails about 20% more energy is consumed by them than on average humans who use electricity. So we calculated out to be about 1,575 kilowatt hours per month that needed to be outputted from our generator. And the final specification our client asked us to do is to reduce the electric bill. So in our motivations objective, our PID controller system was chosen to achieve the following: solve a multi-input and output fuel cell system with 2 or more state variables, identify what input output state variables are, provide a mass energy balance, input and output equations, input and output values, input and output plots for an open loop system, plot step function, plot response, design a PID controller to control output voltage. Introduction: the hydrogen fuel cell are becoming more popular here in the US due to their clean energy. And they're 2 to 3 times more efficient than actual diesel fuel generators. The control system is the backbone of the hydrogen fuel cell. A robust design controls the system is key to an efficient fuel cell. A precise control of input parameters, hydrogen and oxygen, is imperative to a wide range of power outputs. And our primary focus is to control the hydrogen and oxygen system. I will now hand it off to Ishfar to talk about the background.
Okay, so thank you, Michael. So here's going to be our background, and there's going to be a couple of parts to our background. So first off, we're going to talk about the electric generator. So in the electric generator, it takes mechanical energy from an external source, and then it converts that mechanical energy, which is the input, into an output of electrical energy. And afterwards, it will capture the power of motion from the electrical energy and turn that into electricity. And from the electricity, it will force the electrons from its external source through an electrical circuit. And then we'll talk about the hydrogen fuel cell. So in a hydrogen fuel cell, a proton exchanges through a membrane. And then for our proton exchange fuel cell, it'll convert the potential energy that is created by a chemical reaction into electrical power. And then hydrogen will then be provided in the fuel cell through an anode. And then the oxygen will then be channeled through the cathode. Then a reaction will then be created, which will produce the electricity. And then as a result, water and heat will be released as a byproduct of producing electricity. So some of the reasons why we picked hydrogen fuel cell is that for 1 kilogram of hydrogen, it would provide 3.6 kilowatt hours. And then for 1 kilogram of a diesel generator, it would provide approximately 12 to 14 kilowatt hours. So as you can see, hydrogen would provide more energy than a diesel would. And then for $2.32 of a diesel, you would obtain 3.79 kilograms. And then for $2.32 of hydrogen, you would obtain 4.18 kilograms. So as you can see, with a hydrogen fuel cell, you would get more bang for your buck than you would for a diesel generator. And so as a result, we also will have utilized water to create the energy. So some of the ways our fuel cell is different from others is that for our fuel cell, we're going to have a voltmeter. We have some control valves. We have an output that is and what we find out what is needed from it. And we also touch on apartment systems and try to have that apartment be ran by a fuel cell. So these are the ways we have to control our input and output. So for our inputs are hydrogen and air, and the ways we're going to control is we're going to use a valve and a fan to control the amount of hydrogen and air that will enter the system. And then we'll have a feed-forward control system, which will manage any disturbance in the pumping system, and fan that will ensure that the flow is constant for less drops in voltage. And then the feedback control will ensure the ratio between hydrogen and oxygen, which is maintained for maximum efficiency. And then for outputs, we have our electrical energy and temperature. And the way we control it is the PID temperature control system will help in identifying the temperature, whether it's too hot for the fuel cell to safely operate and try to manage it. And then the outputs will then be measured. That is measured will be the electrical energy and power that is produced and the temperature. And so some of the assumptions that we are going to take into consideration is that we're going to have ideal gas. We're going to have uniform fluid properties. Our system is going to be well mixed. We're going to have no phase change. We're going to have no external work. We're going to have incompressible flow. We're going to have a consistent temperature change. We're going to have kinetic and potential energy be negligible. And then our air and hydrogen flow, which is our input, will be assumed to be a step function system. Now I'll pass it on to Abel for the next slide.
So thank you, Ishfar. So I'll be discussing the mass balance equation. So this is just a generic way of looking at how everything is moving from the fuel cell generator, from what it takes in and what it lets out. So our mass balance equation here says the mass flow rate is equivalent to mass flow rate in minus the mass flow rate out plus the mass flow rate of reaction. Due to the system working at steady state, our mass rate of change is equivalent to 0. Mass rate of reaction equals 0. The overall mass balance equation here basically essentially tells us the mass flow rate in is equivalent to the mass flow rate out. So here's our mass balance equation diagram of everything. So basically what you see here is the heat flows in from the hydrogen and oxygen, and it becomes an output. So basically there's an input and output here of the changes that are happening within our fuel cell. And basically, like we stated before, mass flow rate in is equivalent to mass flow rate out for this. Now I'll be passing it off to Javier for the anode and cathode energy balance equation.
Thank you, Abel. Here we have the anode and cathode energy balance on a fuel cell based on the power production, chemical reactions, and heat loss. The general concept of the energy balance is that the enthalpy of reactants entering the fuel cell equals the enthalpy of products leaving the cell, plus the sum of the heat generated by the power output and the heat of loss, as it was explained by Abel Milano on slide 12. Here we're showing the input of the fuel cell equation, and we're at the anode side, and we're also showing the output of the fuel cell at the cathode side, along with the heater reactions from the cathode and anode electrical chemical reactions. Next, please. Here we're showing the input variables into the fuel cell, which is the mass flow rate of hydrogen gas into the anode side and the mass flow rate of the air into the cathode side. Next. Here we're showing the output states of variables, which is the temperature of the anode that it's reading, the temperature of the cathode that it's reading, the voltage output, and the load current. Next, I will pass it on to Anthony Melgar.
So this is the block diagram for our system. It contains all the different components, including the anode and cathode sides, the humidifiers, and the different pumping systems for the cooling system. And for the methodology, we'll be improving the cost efficiency and reduce the hydrogen use. And this will be performed by replacing the anode exhaust system that dumps excess gas into the environment. And this will be replaced with a tank that will be able to store that extra hydrogen without requiring extra ventilation to prevent any safety hazards. Furthermore, the cooling system will be improved by replacing the air generated radiator. And this will be replaced with a heat exchanger that can use a refrigerant like R134A. So the results of the original simulation without any changes is that the stack temperature variations are present within the first 500 seconds, and the power output has a minimum between the last 500 seconds. Furthermore, the fuel tank decreases in pressure from 70 megapascals to 63.2 megapascals, which means that the hydrogen was consumed by the system, but this also creates more work for the pumping system to push the hydrogen through the fuel cell, and a total of 45.5 megajoules of energy were produced. The hydrogen tank was inserted with a purge valve to catch any excess unused exhaust, and the pressure, temperature, and moisture levels were measured. The maximum pressure reached 240 kilopascals, which is easily being able to be stored by the tank safely. And the temperature reaches up to 82 degrees, which is only slightly higher than the fuel cell stack temperature. The heat exchanger using R314A coolant for the cooling system instead of the radiator with air exchange. And the temperature was able to be constant at 80 degrees from 500 to 1,500 seconds. Furthermore, a PI controller was implemented into the pump system to make it more efficient and be able to match any disturbances. With this implementation, the temperature was able to be constant longer at 2,500 seconds for a total of 600 to 2,500 seconds with only 5 degrees Celsius drop in temperature. And I'll hand it off to Abel for the cost analysis.
Thank you, Anthony. So here we made a comparison of cost between the fuel cell electric power generator to the diesel electric power generator. As you can see, the initial cost and installed cost for the fuel cell electric power generator was $12,500, while on the other hand, the diesel electric power generator was $6,000. The annual preventative and predictive maintenance cost for the fuel cell was $2,000, while the diesel electric power generator was $1,200. The annual fuel costs, which would have the generator running 8 hours per day for a year, will be $1,200 on the fuel cell. For the diesel, $3,000. The annual energy savings here, as you would see, is the fuel cell will save you $5,000, while the diesel electric power generator will only save you $1,000. So that's more than 5 times as much energy savings by the fuel cell. So from the results, it can be determined that the temperature drop when changed in electric load occurred, and it can pick it up and it would be wasting fuel. In total, it would take 500 seconds to compensate for the initial change in load and reach the desired of 80 Celsius. The pressure drop of 6.8 megapascals in hydrogen tank produced additional work for the humidifier to maintain a constant temperature and humidity for maximizing the efficiency. Maximum efficiency was rated at 82%. In conclusion, the project was to design an architecture of a controller for a proton exchange membrane fuel cell system. We considered the power management for different electrical loads for the testing purposes in the simulation setting. Our goal was to maximize the efficiency of the fuel cell by optimizing the cooling system and maintaining hydrogen pressure. The project obtained results from the simulation and dynamic equations to determine the flow of hydrogen needed, along with how much intake of air was required. Thank you overall.
Thank you for
guys.
listening.